Hi there. In this video, we're going to be looking at function differentials. We're going to be looking at the derivation of a very important relation that we're going to use in future videos. It forms a lot of the basis of the work that follows. And the relation is day z is equal to day z dx times dx plus day z dy times dy. So where does this relation come from? It can be derived in numerous ways. I think perhaps one of the most interesting ways to do it is to look at Taylor series. So we write Taylor series for this multivariable function z, and we able actually to come up with this relation. So before we start doing that, perhaps we would just do a quick revision of Taylor series. So we have a function z that depends on x and y. And if we want to have some differential change, or rather some change in z, for this change to z in z to occur, there must have been a change in x and y. So it's this change in x and y that has actually caused this change in z. So of course, the change in z is simply just the function with the changes in x and y subtracted by the original function. In other words, we take this z to the other side, and z is of course a function of x and y, so we write minus z, and z is equal to f of xy. So using this equation as the basis, we can now proceed in writing Taylor series. Let's just do a quick revision of Taylor series in one dimension. We're doing a revision of Taylor series. So what most textbooks would do is they would present it as f into x plus h. So this h is just some distance away from x, not too far away, but it's some distance away from x. So what is the function of some h distance away from x? And what it is the function at x plus h times the first derivative at x divided by 1 factorial plus h squared times the second derivative at x divided by 2 factorial, then h cubed times the third derivative at x divided by 3 factorial. So it carries on in this manner, and it can continue in that way forever. So what we're just going to do quickly at this stage is just replace some of these variables relative, because that's what we're going to use in our exercise. So we're going to replace this h with delta x and this f prime with dy dx. So we're just replacing h with delta x and just rewriting this as is. So we're just going to write dy dx multiplied by h over 1 prime, or rather delta x, plus the second derivative times delta x squared over 2 factorial. And lastly, the third derivative multiplied by delta x cubed divided by 3 factorial. So we now extend this to two variables. So the question is, how do we do this? How do we extend this Taylor series in one dimension to that in 2 dimensions? So Taylor series in 2 dimensions. So if we look at our function, we see that we have one variable, right? And it's the derivative with respect to one variable. So if we have 2 variables, x and y, all that happens is that we write the Taylor series for each variable. So for the second derivative, this is the second derivative here, we won't just have the derivative with respect to x, we'd have the derivative with respect to x and y. So we'd have the second derivative day z squared, day x squared, we would have day squared z, day y squared, and also we would have the mixed partial as well. Day z, day x, day y. And you would remember that in the previous video, we saw that there are two mixed partials, day z, day x, day y, and also day z, day y, day x. So what this means is that they're actually two mixed partials, and since they are the same, they are actually equal. So we have two of these mixed partials. So now we can proceed to write our Taylor series in 2 dimensions. So instead of just x plus delta x, we would have x plus delta x and y plus delta y. So x plus delta x and y plus delta y, and this is equal to f at xy, since there's two variables. The analogy is the same, so it's the same series but written for both variables. Then the first term, we have day z, day x, so we would write that down. Day z, day x, and we have the differential day x, 1 factorial, and we would have, for the other variable, day z, day y, delta y times 1 factorial. So now it's just a little bit more complicated when you're writing the second derivative, and how we would do it, I would just continue this here on the next line. We would say plus, okay, so we have this 2 factorial. We're going to write this entire term that you see on this top, the second derivative term, we're going to write it for each of the second derivatives. So writing this 2 factorial, just going to bring that out in the front. We're going to have firstly the second derivative with respect to x. So it's going to be day z, day x squared times delta x squared plus this mixed partial, so there's 2 of them, 2 day z, day x, day y, multiplied by day x, delta x, delta y, and then lastly, plus day squared z, day y squared, delta y squared. And this is going to continue for the third derivatives and fourth derivatives and so on. All right. So can we actually refine this at some stage? So if we just do a bit more algebra here, we can take this function xy to the other side. So we have f x plus delta x, y plus delta y, and we move this along to the other side, becomes minus f xy, and then this is equal to all this stuff. So starting from here, we write this day z dx times delta x, that term, then plus day z day y times delta y, and plus these higher order terms. So it's day z squared, day x, delta x squared, etc., etc. So when we mean higher order terms, we mean these higher order derivatives. We'll just call it plus higher order. higher order terms. What we're going to do is start taking a limit. So when we say we're going to take a limit, we mean that, but before we even do that, if we just look at this term on the left-hand side, if we go to the top, we see that delta z is equal to f into x plus delta x, y plus delta y minus f into xy. And if we look at this term on the right-hand side, we see that it's the same as this term here, what's on the left. So this entire term on the left is just delta z. We can see it. So delta z is equal to all of the stuff on the right-hand side. That's dz, dx, delta x plus dz, dy, delta y plus these higher order terms. So we can now take the limits that I was speaking about, in which we let delta z approach dz. So a change in a small change in z, delta z, now becomes a differential change in z. That means an infinitely small change. So a small change becomes an infinitely small change. So once delta z approaches dz, delta x will approach dx, and delta y will approach dy. All these higher order terms actually cancel out. They cancel out because if we look at these terms, we see that we have a delta x squared. We see we have a delta x times delta y, and we see we have a delta y squared. So what is happening is that we have small changes being multiplied by each other. If we think of a small change, for example, 0.01, and we multiply it by itself, 0.01, a small number multiplied by a small number gives us a much smaller number. So we can imagine that if this delta x becomes dx, an infinitely small number, and we multiply it by another infinitely small number, we're going to get a number that's virtually almost zero. So all of these terms actually can become zero. So we would actually remove them. And if this is true for the second order derivatives, then it will obviously be true for the third order, fourth order, and so on. So all of these terms can be neglected. And what we're left with is that dz is equal to dz dx times dx plus dz dy dy.